Okay, welcome back. So today we're going to finish the proof of the cone theorem. So I copied and pasted the statement that we wrote down last time. So I'll just leave it on the screen for a second so that we can recall exactly what we're trying to prove, and then I'll recap what we've done so far. While we're here, are there any questions? Okay, so far what we've shown is that anytime we take okay, so basically we showed that there's a decomposition of any bar of x into the k greater than or equal to 0 piece plus a countable sum of FLs, where L is some nef but not ample line bundle, and FL is an extremal face cut out by L perp intersect any bar. So it's a face where L equals 0, and where we're looking at the sum over such faces that are just one-dimensional, i.e. these are rays. But they're rays contained in the negative part. So so maybe I'll say it this way: FL without 0 is contained strictly inside of the k less than 0 part, where we call, for simplicity, we just let k be kx plus delta. Okay, and then because L is Cartier, that's how we knew that everything, these rays are rational, and there are only countably many of them. Okay, so we had shown this, and recall the way we did this is by saying take any face cut out by an F divisor. Then we can produce such faces using the rationality theorem, and they're all rational faces. And then we use the rationality theorem again to perturb these faces to cut down the dimension even smaller. And then eventually, if we keep going, we cut it down to these one-dimensional rays. And then we use that these one-dimensional rays don't accumulate away from k equals 0, which again uses the rationality theorem. The fact that the rationality theorem had bounded denominators, we use that to show that these rays don't accumulate. Therefore, since they don't accumulate, then there's only finally many of them whenever you perturb by an ample. And that implies that the left-hand side, the right-hand side, which a priori is not closed, and you need to take a closure, is actually closed. So recap. So let me just say, so we also showed that the statement about perturbing by an ample. And again, where the key point is that this sum is finite because the FLs don't accumulate in that half space. Plus, for any extremal face F, that's contained in the negative part, there's an F divisor D such that F equals FD. Okay, and so now we want to finish. So basically, what do we have left? If we go back to the statement, so we've essentially proved one, except we haven't shown yet that these rays are actually spanned by curves. All we know is that the rays are dual to some F divisor. Okay, we're not going to show this rational part and this bound on the intersection with kx plus delta, just because we didn't do bend and break. We showed two, again, assuming that we show these rays are actually spanned by rational curves. Then we also have two. What we need to do is show three, that there exist extremal contractions corresponding to these faces, and then we need to check that under these extremal contractions, any line bundle that looks like it's pulled back really is pulled back. And the point is that three is going to imply that that these rays are really spanned by curves, because once we have this extremal contraction, then either the extremal contraction is the identity, and then our divisor was trivial, or the extremal contraction contracts some curves, and those curves will span our ray. Okay. So, and that's why we needed this statement that each face really is the face corresponding to an F divisor, because we wanted to use the base point free theorem. Then, by the base point free theorem, so the point is that D is semi-ample. And why was this? Well, we needed to check not only is D nef, but we needed to check that for some A, AD minus KX plus delta is at least big in nef, but really we argued that it's ample, because if you're on this face, well, this face is in the k plus delta strictly negative part. So when we subtract k plus delta, then this divisor intersects, then that portion intersects positively on F, but D intersects 0 on F. So AD minus KX plus delta is strictly positive on F. But then if we move away from F, D is 0, but sorry, if we move away from F, D is not 0 anymore. D is strictly greater than 0, because F is exactly the portion where D is 0. So as soon as we move off of F inside of the effective cone, then D has to be strictly positive, and then it doesn't matter what KX plus delta is, because we just make A large enough so that the whole expression is positive, and so we get that this is ample because it's positive on all pseudo-effective classes. Okay, so then we said, so by base point free theorem, we have some phi BD isomorphism for large B, and then taking the Stein factorization and taking the Itaka fibration for as B gets larger and larger, plus Stein factorizing. Maybe that's already part of the definition of the Itaka fibration. Then we get our extremal face, of course, our extremal contraction phi f from X to Z, which is some projective morphism with Z normal. Such that, well, yeah, Z is normal. More generally, phi f lower star of OX is OZ. So phi has connected fibers, and the important point that phi of C is contracted to a point if and only if the class of C is in our extremal face. And then we said that these conditions actually uniquely characterize phi f. because the second condition tells you what Z is as a topological space. It's exactly the quotient of X by the equivalence relation. All points on C are all points on curves in our face are identified. And then the first condition equips it with a structure sheaf, so it gives it the structure of a scheme in a unique way. Okay, so that's all good. Now we have our extremal contractions, and we know they're unique. So in particular, so write it this way: if phi f is not the identity, i.e., f is not the zero face, then phi f contracts some curve, and let's say, so for this statement, let's say we're at the level of rays actually. So let me add that. So suppose f is one of these rays, which we already said were the form FL, rather than just an arbitrary face. Then phi r, since we're assuming we're on a ray, so it's not zero, then phi r actually contracts something, and so there are curves, some curve C, and so by condition 2, that implies that C, the class of C, is in our ray, so our ray really is spanned by the class of an effective curve. Okay. Yeah, which you should think really illustrates the strength of these of the space point free theorem and the space point free method, because I mean, we saw examples where there are rays on the boundary of the cone that are pseudo effective but not effective. There are actually no effective curves there, and the point is this just can't happen on the negative side of the cone. It's pretty amazing. Okay, so now we want to check the statement on line bundles. So if I pick up with the notation from before, this statement here, that for array it's really spanned by a curve, was step 8 in the proof, and now step 9 is showing that if we have a line bundle that's 0 on all these curves, then it's pulled back. So first we start with some d that's nef, such that the corresponding face is our given f. Then what do we know about this d? Then this d satisfies the assumptions of the base point free theorem, just like before. And the point is we can just pick some other d. But then by uniqueness of this Itaka fibration, for any given d that's supported on this face, this uniqueness of phi f implies that the base point free, or that the Itaka fibration of the base point free map BD for large B is the same as this phi f. So any D that's supported on this face gives you the same extremal contraction phi f, because the extremal contraction is unique. But that tells you that this D has to be pulled back. Well, okay, so really, I should say one more thing. We really know that kind of for large enough B, it's pulled back. But the point is, it doesn't matter which large enough B I take. So I can take B large enough and then B plus 1. They both, because once I stabilize, then I get the same morphism. Then BD is pulled back, B plus 1D is pulled back, so D itself is pulled back. Because the morphism is just unique. Okay, so that tells us that at least all Neff divisors that vanish on our face, that vanish exactly on our face, are pulled back from Z. And now we're going to use those to pull back all other divisors that vanish on our face. So if L is any divisor that's not necessarily Neff, but satisfies that L dot C is 0 for any curve with the class in our face. Now we want to show that this L is also pulled back, and we know that all such D are pulled back. So we again pick our favorite D that gives us this extremal contraction, and then we look at MD plus L for M very large with D as above. Then if we consider this MD plus L, so we know that MD plus L is 0 on our face because both D and L are. And we also know that, well, L dot things away from our face could be anything. But the point is we know that D dot any pseudo-effective class is strictly positive for anything not on our face. So MD plus L is Neff for large L, for large M, sorry. And so it also induces, so it's a Neff divisor that vanishes exactly on our face. So it also induces the same linear series as phi F. And so by our previous observation that Neff divisors that induce this extremal contraction are all pulled back, we know that MD plus L is the pullback of some divisor dz prime. And so L is the pullback of dz prime minus mdz, where dz is the thing that pulls back to D. So it's also the pullback of some Cartier divisor. Okay, so really this hinges on the fact that this extremal contraction is unique. Any questions about that? Okay, and now we get a nice corollary just from this step that I'll record here. So let's say we have the contraction of a ray. Then we have an exact sequence, or let me just write down, then the following sequence is exact. So if we look at pick Z pulling back to pick X, and then what's the co-kernel? Well, we just have array, and the co-kernel is just a copy of Z. well, it's not the co-kernel, but the next thing in the exact sequence is a copy of Z, where this map is just a line bundle goes to L dot C, which is some integer. Okay, so the claim is this is exact. So Z isn't necessarily co-kernel. It's not exact on the right, but it's exact in the middle and on the left. So there are two things we want to check. We want to check that phi f upper star is injective, and that L is in the image of phi f upper star if and only if L dot C is 0. The second statement is just exactly what we proved up here. It's exactly part C of the cone theorem. So we just need to check that phi f upper star is injective, since exactness in the middle was step 9. But for phi f upper star being injective, we can use the projection formula. So we also have this map phi f lower star, which a priori sends line bundles on X to some coherent sheaves on Z, not necessarily line bundles. But if we apply it to the pullback phi f upper star of some L on Z, but then by just to be consistent with my notation, let me call it OZ of L. Then by projection formula, this is the same as OZ of L tensor phi f lower star of OX, but by our property of our extremal contraction, this is just OZ of L, because phi f lower star OX is OZ. And so phi f lower star gives us a splitting of that first map, so it's injective. Or maybe it doesn't give us a splitting, but it tells us that we can distinguish the pullbacks of line bundles from Z from each other, so it's injective. So it only really gives us a splitting on the image of big Z, but. Okay, so that's a nice corollary, and the reason we wanted to single out specifically the extremal ray case is because then we get the following equality that should look a little familiar, which is that in particular the Picard rank of Z is the Picard rank of X minus 1. So this is the analog of in the case of surfaces where we argued that we get minimal surfaces by blowing down -1 curves because the Picard rank keeps dropping. So ideally, we'd want to use this corollary to say that by applying extremal contractions of rays over and over again, we get some nice minimal model because the Picard rank keeps dropping. And we'll see that there's an issue here because of flips, but at least we have some partial progress toward that. Okay. Okay, so that actually concludes the proof of the cone theorem. Modulo the stuff we didn't prove, which is that the curves are actually rational. So I can put that here actually. Okay. And so now we get another corollary, which is just the analog of our classification of extremal contractions, just in the log case. So there, if you recall from a couple of weeks ago, we needed to make an extra assumption on our pair, which was that it was Q factorial. So, or a couple of weeks ago, there was no boundary divisor, it was just an X. But so suppose X comma delta is a projective Q factorial KLT pair. And R is some k plus delta negative extremal array. Then the extremal contraction phi r from x to z is one of the following. Well, either one, it's birational with exceptional divisor E being an irreducible, or with exceptional locus being a pure irreducible divisor. I'll just say irreducible, I guess, because we're really taking the reduced exceptional locus. Or it's a small birational map. So a birational map that contracts no divisors, the exceptional locus is higher codimension. Or it's not birational, and so the dimension of z is strictly smaller than the dimension of x. And in this case, phi r is what we maybe can call a log Fano fibration. Okay, and so this is exactly the same as before. There's really the only things to check are that one, if it's birational and contains a divisor in the exceptional locus, then that divisor is the full exceptional locus, and that's where we use the Q factorial assumption. It's exactly the same argument as before, just with a k plus delta there instead of a k. Or it's small birational, okay, that's it. Or the dimension of z is smaller, and then the only thing to check is that it makes sense to call it a log Fano fibration, but that's just saying that if we restrict kx plus delta to the generic fiber, so let's say f is a generic fiber in case 3, or maybe I'll say general fiber, but it doesn't matter. Then we saw this argument before that by adjunction applied kind of over and over again. When we restrict to the generic fiber, kx plus delta restricted to f will become kf plus whatever delta restricted to f is. But if f is generic, then delta restricted to f will be some KLT pair. And so the point is that then x comma delta f is some pair, or at least delta will be a boundary. I guess we haven't checked that it's actually KLT, but at least delta will be effective if we take f generic. So if we just take some f that's not contained in delta. So is a pair with minus kf plus delta f ample, because kx plus delta is ample on the fibers of phi. So is anti-ample on the fibers of phi. It's kx plus delta is strictly negative on the fibers of phi. So minus kx plus delta is strictly positive. So when we restrict it, we get something ample. And so if you recall, Fano varieties are varieties where minus k is ample. So here we can call these log Fanos because they're pairs where minus log canonical is ample. Okay. So that gives us our basic building blocks for our extremal contractions, and it gives us description of our various steps in the minimal model program. One more corollary, which is that if we're in case 1 and 3, then the situation is nice. Then we can just keep going on Z and apply the cone theorem again on Z and keep producing more and more extremal contractions. So more precisely, let X comma delta be a projective KLT pair again. And R an extremal array. Again, let's suppose that X is Q factorial. And suppose that the contraction of this R is either case 1 or case 3. Then, or sometimes maybe people use the language here that it's a fiber space. Maybe a Mori fiber space for case 3. Then Z itself is actually Q factorial. So contrast this with what we said in the case of 2 when we have a small birational map. So we did this when there was no boundary, but we showed that for a small birational map, when you just have an X and no boundary, then Z just can't be Q factorial. And it's the same exact thing here. If we have the small birational map, even with a boundary, then again the Z just cannot be Q factorial. And in fact, the like log canonical can't be a line bundle. But the nice thing is that if we're in case 1 or 3, then Z is still Q factorial as long as X is, and so we can hope to keep applying all our theorems to Z. Okay, so let's prove the corollary. So let's just do the 2 cases separately. So in case 1, phi f is divisorial. We want to show that any Vey divisor on Z is actually a Cartier divisor, and we're going to use the fact that we know which divisors on X descend to like which line bundles on X descend to line bundles on Z. So we're just going to show that whatever our B is downstairs, it's linearly equivalent to something that's descended from a line bundle upstairs, and so it has to actually be Cartier or Q Cartier. Okay, so let's say it's divisorial, and then let's say E is the exceptional divisor. Then, well, we know that by the negativity lemma, because E is an exceptional divisor of a birational map, then we know that E dot R is less than 0, where R is our ray. So I should have an R there as well. So now pick B, or just let B be a Vey divisor on Z. And now we'll consider the strict transform of B plus some rational number S times E. And now the point is that because E dot R is non-zero, Well, the strict transform will intersect R, like the curves in R, to be something. So here we're using that R is generated by a single curve. So we know that if the strict transform of B dot C will be some number, we know that E dot C is not 0. So we can pick an S so that this dot C is 0. But then this phi F lower star inverse B plus SE, whatever it is Q Cartier because X is Q factorial. So we pick some M to make it Cartier, and then by the cone theorem, we get that this is the pullback of some divisor MZ, where MZ is Cartier. Okay, and then the point is that that then B as a V divisor is Q linearly equivalent to 1 over M MZ, because both this MZ and this B have to be linearly equivalent away from the exceptional locus of phi. But that's a codimension 2 subset. So if they're linearly equivalent away from the codimension 2 subset, then they're linearly equivalent. So then B is a priori with some V divisor, but it's Q linearly equivalent to some Q Cartier divisor, so it's Q Cartier. So. Since the exceptional locus is codimension 2 on Z. Or more precisely, maybe we'll say the exceptional locus of phi inverse is codimension 2. Okay, so that gives us the divisorial case, and now we'll do a similar argument for the fiber space case. So suppose dim Z is less than dim X, and B again is some V divisor. On Z, then there's some locus, because Z is normal, there's some large locus on Z where B is actually Cartier. So there's some. And the complement of this is codimension 2 in Z. So now we consider the pullback of this Cartier divisor, B0, just restrict to this open set. So this B0 is going to be some U intersect B, where this is some big open set, where we call big means that the complement is codimension 2. So now we can restrict phi to the preimage of U. I keep writing phi F instead of phi R, but just remember this whole time F is actually array. And now, because we're on this locus where B0 is Cartier, it makes sense to pull back B0, because now it's a Cartier divisor. And then we can just take its closure. And that'll be some divisor D inside of X. But again, X is Q factorial, so MD is Cartier for some m. But on the other hand, D is, or at least generically, is pulled back. So if we look at the generic fiber of phi, then D is just pulled back from Z. So MD dot a generic fiber is 0. But here we again use that we're on array, so it's spanned by a single curve. So whatever that single curve is, there exists some class in the generic fiber, some representative of that class in the generic fiber. So MD dot C equals 0 for C spanning the ray. So you can imagine kind of what could go wrong. Though I think in the end it's fine, but you can imagine what can go wrong if you don't have a ray but have a higher dimensional face. Then you get that MD.C is 0 for something on the generic fiber, but maybe you have extra classes that are only in the special fibers because you're not spanned by a single curve. But because we're in the case of array, we just have a single generator, and so that single generator lives in any fiber we want. So then MD is the pullback of some Cartier MZ. And so again, just like before, this B and MZ over M are linearly equivalent on this open set U, so away from codimension 2, so they're linearly equivalent as Vey divisors. But since MZ over M is Q Cartier, then this implies that B is Q Cartier. Okay. Any questions about that corollary? Okay, so one more corollary. Again, let Phi be an extremal contraction now, not necessarily for array. And suppose X delta is projective KLT. Delta is effective, so all the assumptions we needed for the cone theorem. Then we have the following vanishing. The higher cohomologies of the structure sheaf are 0. We also know that the push forward of the structure sheaf is just the structure sheaf. So another way of writing this is that if we think of the complex, this derived push forward of OX, which is some complex in the derived category of sheaves on Z, then this is quasi-isomorphic to OZ, because we know on level 0 it's OZ, and then everywhere else is just 0. So this is maybe another way you might see this condition. And what does this really tell you? It tells you that via the Leray spectral sequence and the projection formula, that kind of cohomology of line bundles you can compute on either X or on Z. So it's very useful for various computations, and it also tells you that, or it's kind of hints at this fact that if there's time, we'll prove later that KLT singularities are rational. Okay, and then the proof is actually just relative Kalmanovic vanishing, because we know that minus kx plus delta is phi f ample. So we let D be the zero divisor in column out of V vanishing. So 0 minus kx plus delta is Phi f ample. So by kV vanishing, the push forwards of OX of D, which are just OX because D is a zero divisor, are 0. Okay. Okay, so next we want to see that we can extend all of these results to the relative setting, where instead of having a projective variety, we have some variety that's projective over some base. So the first thing, we want a relative base point free theorem. And we'll see that the interesting thing is that to prove the relative base point free theorem, we actually need the cone theorem in the absolute case, which is kind of interesting. So let x comma delta be a KLT pair with boundary delta. And let's say f from x to y is a projective morphism. And let's assume y is a variety. So at the least, we probably want to assume that it's like separated finite type, but let's assume it's really just a variety. Well, in the base point free theorem, we have this Neff divisor. So in the relative case, we should have an F Neff divisor. So let's say D is an F Neff Cartier divisor. Such that AD minus KX plus delta. In the usual statement, this should be big and F. So in this case, we want to say that it's F big and F Neff for some A. Yeah. Then D is F semi-ample. Or another way, so okay, I don't remember if we really defined F semi-ample, but it means the same thing, that BD is F base point free for B much larger than 0, and then you can ask the precise definition of being F base point free. It means, well, generated by global sections, but now global sections are relative to F, so i.e. the natural map like this is surjective for all B greater than 0. Okay, so that's the relative base point free theorem. So we'll sketch the proof. So the first ingredient is to compactify and resolve the situation. So we'll compactify, extend our divisor to the boundary appropriately, and resolve our morphism so that we can reduce to the case where we have a morphism between projective varieties. So maybe the step one is going to be the sketchy part of the proof. Okay, so maybe here I should have assumed at the very least that y is quasi-projective, not just a variety. But really, even then, some of these assumptions can be dropped. It's just I don't know. They can't always be dropped. Sometimes they can, sometimes they can't. So might as well just assume quasi-projectivity everywhere. Okay, and the point is that this condition, all these conditions, fnf, f big, and f base point free, are local on y. So if we can find some compactification and extend all our divisors so that on the compactification we get the statement, then by just restricting to the open set y, we get the statement for that we care about. So that's some other rough idea. Once you find a compactification where everything extends and all the assumptions are satisfied, then that's good enough. Okay, so step 2, now we're in the case where we have a morphism between projective varieties. So let's say A is an ample on Y. Then the claim is that it suffices to show the statement for the divisor D prime given by D plus the pullback of the sample. And actually, we'll say more. It suffices to show something slightly different. It suffices to show that that for this D prime, when we pull back the sample, how do I want to say this? It suffices to show that this D prime itself is actually base point free, not just F base point free. So it suffices to show this a priori stronger statement that some divisor is actually globally base point free rather than just locally on Y. Or some large enough multiple, because of course we're showing something semi-ample, so we're showing some large enough multiple space point free. So indeed, the point is that if we have this, if we know that MD prime is base point free, then we know that for any x, we know we have a section S in H0 x MD prime that doesn't vanish. So with the condition S of x is not equal to 0. But now whatever this x is, whatever this point is, let's just pick some neighborhood of f of x. And look at its preimage. And so then this x sits in there. But pick our u to be a trivialization of O y of A. So then on our u, the A piece is just trivial. So when we restrict to the preimage of this u, D prime and D are the same divisor. But then here we've produced actually a global section. We're assuming that we have a global section that doesn't vanish at x. So in particular, we also have a local section. So let's also just assume that this is affine. So maybe more precisely, then when we restrict to well, this is first isomorphic to H0 on Y of the push forward. Which then we can restrict to our U. And when we restrict to our U, this A goes away. So this is just some section of the push forward of MD restricted to U, which is the same as a section on V of MD restricted to U. And so we've shown that if we assume that D prime globally has sections that don't vanish at X, then D locally has sections that don't vanish at X, i.e. that it's space point free. Okay, so sorry I kind of bungled that a little bit, but are there any questions about that step? Okay, so then we just want to check that we can apply the usual base point free theorem to this D prime. And that was the point of compactifying in step 1, to reduce the local question to something global where we already know what to do. So then by assumption, AD minus KX plus delta is F big. So then if we add some pullback of some ample or some hyperplane H, then this is big if H is ample enough. So essentially, what's going on here? Well, F big means that the push forward has that the rank of the push forward of our line bundle grows like the dimension of the fibers. But then we're twisting by this very large ample, and so eventually we'll get so downstairs we'll get some vector bundle of the right rank that's twisted by some large ample, and then Riemann Roch will tell us that the growth rate of sections of that vector bundle, because we're twisting by this very large ample, is what you'd expect. And so then the sections of the push forward are the dimension you'd expect, so the sections upstairs are the dimension you'd expect. That's roughly the idea of the step, but I'll leave the verification for you to check. So now, because this is big, then we know that it's of the form ample plus some effective. So we'll just pick some E effective such that AD minus KX plus delta plus F upper star H minus epsilon E is ample. And now, because we have this epsilon here, then we can make epsilon small enough so that the pair X delta plus epsilon E is KLT. And so then we let A just be H divided by little a, this is A in front of the D, and then let D prime be D plus F upper star A as above. So then what do we have? We have that X comma delta plus epsilon E is KLT, and D prime minus the log canonical, AD prime minus the log canonical of this new pair, let's call this delta prime, is ample. Particular, it's big enough, so D prime is semi-ample by the usual base point free theorem, which is exactly what we claimed we needed. Except I forgot one one important step. So here we know that AD prime minus KX plus delta prime is ample. We needed one more assumption in the base point free theorem, which is that D prime itself is nef. So I really should say, so if D prime is nef, then it's semi-ample by BPF. So we really have one more step, which is to check that we can arrange it in the situation so that D prime is actually nef. Okay, so because right now all we know is that it's an F and F divisor plus the pullback of an ample. And here's where we really need to use the cone theorem. So step 5, need to check that D prime can be made nef. So in general, it's just not true that that if you have an F-nef divisor, that an F-nef divisor plus the pullback of an ample is actually nef in general. Because kind of you don't know how negative D is away from the fibers. All you know is that it's not negative on the fibers, but there could be a lot of curves that are just away from that are not contained in the fibers where you just have no control. Okay, so so now we apply the cone theorem to x comma delta prime. So we get that there are finitely many rays that are contained in the kx so we want to perturb by some ample, and now I'm a little confused. Right, so we let the ample be exactly this one here. Sorry, so we said that this is, we've constructed things so that's an ample. We let that be the ample that we're perturbing by to get finitely many rays. But then if we look over here, this is exactly A times D prime, right? Kx plus delta prime plus G, where G is some ample, is exactly A times D prime. So this half space where this is negative is the same as the half space where D prime is negative. And so the point is there are just these finitely many curves where D prime is negative. Because D prime is F and F, they're all contained. None of them are contained in the fibers. They're all kind of horizontal to the fibers of F. So since, since D prime equals F and F plus a pullback, then if we write these rays as R greater than or equals C, then these C's are not contained in the fibers because they're where D prime is strictly negative. And since there are only finitely many of them, then by just pulling back more and more ample A, we can eventually make them non-negative. well, okay, and then the point is that because we know they're not contained in the fibers, then we know that C times F upper star A is push forward of C times A, which is strictly greater than 0 because A is an ample downstairs. So by making A more positive, we can make d prime dot C greater than or equal to 0. Because the D part is fixed. So I guess that's important. We have these finitely many curves where D prime could possibly be negative. There are most finitely many. But we're only adding multiples of A. So whatever the intersection with D prime is, it's some negative number of the form intersection with D plus the intersection with the A piece. And the D piece is always fixed because D isn't changing. And so if we keep increasing A, eventually we'll make them all non-negative. Okay, so that tells us that, so by modifying our A, but it didn't matter which A we picked in the end, we can make D prime F. And so that lets us apply the base point free theorem to see that D prime is semi-ample, and then by our previous step, that tells us that D is F semi-ample. Okay, so that's the sketch of the relative base point free theorem. Then from there, since there's no time today, we'll do this next week. But from there, we can prove a relative cone theorem, and then we'll start actually running the minimal model program on pairs.